we're going to talk about thin film interference. And one of the requirements for an interference pattern to happen in the stable interference patterns would be a coherent wave. And coherent has two requirements. One would be the two waves that are getting the stable interference have the same frequency and they have a constant phase relationship. So they're not random phased relative to each other, and that phasing is not changing. And we're looking at the two most extreme cases: one that they're totally in phase, and the other one that they're totally out of phase. Now, coherent waves often come from a single source, or they could come from related sources. A single source would be a single light where there's two slits, and then it breaks into two different waves, but it comes from that same source. Or a related source could be, example, if we think about sound waves interfering with each other. If I had two speakers and those are my two sources, and if they're connected through wires to the same stereo and the music's coming out from both the speakers, well then that output would be coherent because it's coming from the same source. And now for the extremes, in phase results in constructive interference. And so what I've drawn here is a wave at a frequency, and there's the wavelength. That's wave number one. If I take wave number one and just start to move it in a certain length until I get constructive interference, well, I have to move that length essentially one wavelength. So I take this wave and just slide it over one wavelength, and I could create wave number two. And now wave number two, if I look at wave number one and two, if I look at any point, any distance that they are, and add they're up, this plus the peak plus the peak is twice the peak. So they sum up to add something which has twice the magnitude as any of the incoming ones. And so if this was visible light, this would result in a bright interference pattern, because they would be constructive. The extreme opposite, would be destructive interference. And it's gonna have this first wave, and here's this wavelength, and I'm gonna slide it a certain length. And this time, if I move that length half a wavelength, so take this wave, I moved it half a wavelength. Now you can see the result is when the first wave had a valley, this one had a peak, and so if I add any length, I add them up. Now I get nothing. So they're both waves together have magnitude, but add them together and there's no magnitude at all. So they're destructive. And so if this was something in light, if this is a visible light type thing, when in the region where it's destructively interfering, it would be dark. Now for thin films, we kind of this delta length difference being a full wavelength gives you constructive. Shows up in thin film interference. So if my delta length, that one of the waves has to go relative to another wave is a integer number of the wavelength, then I will have constructive interference. So if delta L is an integer number, well, actually it could be no shift at all, or 1, 2, 3, etc. times the wavelength, then I'll have constructive interference. But for thin films, these integers doesn't go to infinity, because the construction only works for a certain amount. So we're only going to consider thin films, and so this m doesn't go to infinity. And so therefore constructive happens when this delta length change is either 0 or 1 wavelength or 2 wavelengths or 3 wavelengths, and it must be the wavelength of the wave in the thin film media. And then as shown right here, destructive interference happens when that first one is when I'm at half a wavelength. And then at half a wavelength, and if I add another one wavelength to a half of that wavelength, I get 3 wavelengths over 2, which is also 1.5 wavelengths, or 5 wavelengths over 2, which is also 2.5 wavelengths. And so this would be the formula. So it's a half. So m can be 0, 1, 2, 3, etc. And so that result in this amount of destructive interference, wavelength length differences in the travel of these in the thin film of these waves, so I get constructive or destructive. And then just as a quick review to understand some other mechanisms that create interference, the double slit diffraction grating is another mechanism besides the thin film that can create interference pattern that's constructive or destructive. And the thin film and the double slit one is the simplest. This is the simplest, and then we'll talk about single thin slit is a little bit unique compared to it, and then thin film is kind of like double slit, but there's one more layer of complication. So double slit, if we just recall, so either double slit or diffraction gratings are if I have a signal coming from a wave coming to a source to a thing that has two slits, and then on the far side of the slit, for example, there could be the waves will continue and have an interference downstream. And kind of like this, if the distance from one slit to where they interfere is one wavelength, or the length difference from one slit to the other slit at a point in space is one wavelength, then they will constructively interfere. So if that delta L is one wavelength, so m, and m could be 0, 1, 2, 3. So if it's m is 0 means the point between the slits. Okay, that would be bright. And then if it's one wavelength difference, then that also be bright. And then half a wavelength difference is they destructively interfere, so it'd be dark. And so at integer numbers of wavelength differences in delta L, we'll have constructive interference. And so here's kind of the formula showing it. So where lowercase d is the distance between the slot centers, I can find a sine of an angle to where they interfere constructively and are bright, and that's my integer numbers of my wavelength. And then every time between there is destructive. So this formula, d sine of theta equals m, where m is, so this would be 0 or 1 or 2 or 3 wavelengths, give you constructive, and then every time in between there is destructive. And so this d sine of theta equals this integer m times the wavelength. And on these graphs, it shows the results. The x-axis is the sine of theta, where for the case for the double, so here's the picture of it. I have a surface here which has the double slits, and the perpendicular to that is where I measure theta off of. So theta equals 0 would be right between on this perpendicular between the two slits. And the same thing for a single slit, it would just be one slit, and a theta of 0 would be on a line perpendicular to that single slit, with the surface with the single slit. And you can see that at 0 and at 1 wavelength over d, that would be bright, and then two wavelengths over d would also be bright, and then in between there it would be dark. So that's kind of helps us understand what's going on here. And now for a single thin slit, I'm going to show the results. I'm not going to explain the theory behind it, because that would take too long, or do the geometry, so we'll just present the results. So here's my single slit. The width of the slit is d. It's a thin slit, and again, my right between is my center, and that's I have a perpendicular to that slit, and my angle theta is measured relative to that. And there's my interference pattern I can see right there, and we'll kind of zoom up and see it right here. Again, right in the middle, where it's equal distance from this corner that edge of that one slit to that center and equal distance there. So they hit those two edges of that single wide slit, or it has to be very thin, and the center again is bright. Okay, so that's what we'd expect. But this time we don't have the destructive interference at half the wavelength and a constructive interference at a full wavelength of d sine theta. Instead, I have a wider band of this first bright, and my first destructive interference is at the d sine of theta equals one wavelength. So in this case, m doesn't have 0. The first destructive is m equals 1. Here, the first destructive is m equals a half. So that destructive, that center wide bright zone with a single thin slit is wider, and it pushes the first destructive to now, so that now destructive interferences happen in integer numbers of d sine theta of the wavelength. So where d sine of theta equals 1 theta and d sine theta equals 2 theta, those are now destructive, whereas for diffraction grating or double slit, the integer number of wavelengths in the lowercase d, which is the distance between slots, those were constructive. Here they're destructive. So there would be darkness there. And so it's a little complex, and I won't explain why it is in this video, but you just have to see that there is a significant difference in how the pattern of a single thin slit compares to the double slit and diffraction grating interference patterns. With thin film interference, unlike the other interference generating mechanisms like double slit or diffraction grating or single slit, one must consider a possible 180 degree or pi radian phase shift with reflection at the boundaries of the thin film and the media on both sides of the thin film. So in addition to this delta length difference, we can have a possible phase shift of pi, which happens because of reflection, but it happens because of differences of the index of refraction of the two media. The media in the thin film and the media on both sides of it. And actually there can be two different medias on both the sides of the thin film. And we'll go through examples to talk about that. Now, refraction itself never produces a phase shift, but the index of refraction changes does a reflected wave have a phase shift or not? So reviewing just quick, the index of refraction is lowercase n, is the ratio of the speed of light to the speed of a wave in a media. And therefore you can just rearrange that and get the speed of a wave in a media is the speed of light over the refraction index. And therefore we know that nothing can go faster than the speed of light, so we know n is always greater than or equal to 1. And therefore the speed is always less than the speed of light, unless it approaches, when it's 1, that it is the speed of light. And so the higher the refraction index, the lower the velocity. So there's two cases when I have a wave going from one media to the other. So one case would be that the media that the wave is first in has a lower index of refraction, therefore going higher velocity than the media that, so here's a media 1 and a media 2, there's a boundary, this wave's coming to it, First it's traveling in the media that has the low index of refraction going fast, and then it's coming to the the second media, which has a higher index of refraction, and therefore the velocity of that wave is slower. So in this case, I've shown this wave coming in here, has an incident angle at the boundary, and then it reflects off an angle of incidence, angle of reflection, because I have some reflected, and then I'm showing I have some refracted, and using Snell's law, we know that when I go to a index of refraction which is higher, that this wave bends towards the normal. And this wave coming from here, there's no phase shifting. So this has a certain phase, and this just continues on at the same phasing. Now the wavelength changes in this new media, but there's no phase change. So if it hits it at a peak, it just keeps continue on at the peak. The amplitude can change, the wavelength changes, but the phasing doesn't change what's refracted. But as far as what's reflected, if the media that's in has a low index refraction and it hits a media that's a high index refraction, for example here it's an air and it goes to glass or water, then this reflected wave has a immediate 180 degree or pi phase shift on the part that's reflected. So it's coming in and it has a wave, and say it's at a peak, the reflected part of it immediately jumps to become a valley, and it continues on going this way. So there's a 180 degrees phase shift, which we must account for to understand is it can constructively or destructively interfere with the wave that hits the backside of the thin film and comes up. So I must account for that phase shift there. Now the opposite case happens when I'm in a media that already has a higher index of refraction than the second media. So for example, in water, it's coming to air. So I'm in the low velocity media, and then I'm going to the media that has the higher velocity electromagnetic wave speed. So in this case, again, I have this wave coming in, and again, there's never, so using Snell's law again, going to this, for example, to the air, from water to air, the high index of refraction to low index of refraction, I move my angle, refracted angle, away from the normal. But this, again, the refracted one never changes phase, just keeps going. In this case, the reflected wave doesn't, so I'm at a certain phase on the incoming wave, there is no phase shift on the reflected wave. So it's coming in, and for example, it's at a peak, it'll continue at that peak and just go reflected on and continue on its way without that phase shift. And so we know now that there's two cases. One, if I'm going from a low index of refraction to a high index of refraction, the reflected wave experience a pi radian or 100 degree phase shift. If I'm going from a high index of refraction media to a low index of refraction media, the reflected wave shows no phase shift. So now we're going to have three examples of different conditions of films that have thin films that have different conditions between the index of refraction of the media on both sides of it, and see how that affects how thin the film must be in order to cause constructive or destructive interference.